Okay, thank you, Phil. Welcome to my talk. More dimensions. You may wonder what this title is all about. It's one of those titles that you can choose, and then the night before you can decide what you're going to talk about. And that's exactly what I want to do. It's maybe still floating. I don't know what's going to be in this talk at the very end, and I hope to entertain you now for 30 minutes before we go for the food processing. All right. The talk is roughly structured according to the dimensionality of the data. Data come in all kinds of dimensions. You may be very well aware of. You have one-dimensional data like sound or time series. And there are two-dimensional data like images, three-dimensional data like volumes or movies. And then, of course, there are n-dimensional data that may not be perceived as such, but as soon as you have a data set and you create all kinds of features, these features create an n-dimensional feature space. And you can then also apply all kinds of mathematical routines, as you will see in this conference, on these n-dimensional feature spaces. All right, the current table of contents as of now is the following. I will start up with some subtle differences between event series and time series, which is our format for one-dimensional data sets. Then I'll apply those to do some forecasting. Since we're here in Frankfurt, the city of money, I will try to do some forecasting regarding precious metals. So you can try to get your expenses again back in. Sound processing, I will try to measure the speed here on the Autobahn via Doppler effects. I will do give some examples about resampling theory and all the built-in resampling methods that we have, taking here the example of B-spline interpolation. Then I will do a very simple, fun example, processing the images of a fish tank. Then I'll do some image processing, so some 2D signal processing by removing and adding image data, by doing image restoration, and then eventually go to 3D images, that is 2D images plus time, so looking at animations. And I will try to do motion magnification. And last but not least, just as a kind of a final remark, I will again mention the future of all of this, which is eventually deep learning, as you have seen in previous talks today about image identify. All right, let's just get going, utilize the time. Okay, there is a subtle difference between what's called an event series and a time series in Mathematica. An event series is basically good for data that does not have intrinsic interpolation. So the typical example for this are, okay, let's see if I have connections to the internet. I hope so. Are earthquakes. Well, earthquakes are fairly discrete events. No, it doesn't seem to ring a bell, so let me just quit this and use the pre-loaded data. Earthquakes are discrete events, and so it doesn't make any sense to interpolate between two earthquakes. I mean, either there is an earthquake or there's no earthquake. So an earthquake should be an event series. Unfortunately, earthquakes currently come into Mathematica as a time series, which is, strictly speaking, a bug. But I can rectify that very quickly in Mathematica by wrapping event series around earthquakes, and then I have actually an event series object, in Mathematica, as you can see here, and I can visualize that. And here what you see are now the earthquakes in the metropolitan area of Tokyo from 1950 until the beginning of this year. And you can see there are irregular, so these are not regularly sampled data, they are irregular sampled data, and they are discrete. So what I can do, for example, with this kind of data, I can translate those into energies. These are the magnitudes of the earthquake according to the Richter scale. So I get here now time event series for the energy. I can plot that again, and that gives me a much more dramatic picture of what's actually going on, how much energy is released in this area, in joule, by the way. And then, just as one example of many filters that we now have for time series or event series for regularly sampled or irregularly sampled data, is now here a mean filter that basically takes the average over a certain time span that I can specify here, either in seconds or as a quantity. Here, for example, I'll have a radius for that mean filter of half a year. And it will just take the average magnitude or the average energy of earthquakes within a year. And then I can plot those two. And what it does basically is it does not weigh that data with the time of the event, but just the magnitude or the energy itself. In that respect, it just looks at the discrete events without looking at the time span in between. This is now for event series, and the subtle difference I'd like to point out is now in contrast to time series. Time series are now measurements in time where in principle you could talk about an interpolation. Basically, if you have an observable that is continuous, then you typically would have a time series. And now I have a connection. In case you haven't been outside, it's 19 degrees outside here in Frankfurt. Temperature is a typical continuous observable, but the measurements you'll do most likely will be discrete. So we have for that the object, the time series object, and the time series object basically comes with its own interpolation recipe. First of all, of course, you have discrete data in there, but underlying the idea is it's continuous, and as I said here, down here, you have a resampling method built in, and in this case, it says it has a linear interpolation as a built-in model. And the neat thing now is that if you process such a time series in Mathematica, it takes that underlying model into account. So if I now take the mean filter on this, it does not take the average of time measurements in a certain time interval, which may go terribly bad because they are irregularly sampled in this case, but it basically constructs the underlying interpolating function and then basically integrates over a certain time area, so it weighs the data according to the time steps in between. And then I can do that automatically here just by calling up mean filter on the temperature, specifying I want to have a 6-day averaging window, and these are now the averaging temperatures in Frankfurt in the month of May. Okay, let's try to take or bring, make something sensible out of time series. It's one thing to talk about the past, it's a completely different thing about talking about the future, especially when it comes to financial objects. And here, I'd like to quickly load into Mathematica the value of silver, gold, and platinum from the date 1st of January 2013 until yesterday, the 1st of June 2015. So I'll just load them here one by one. Okay, lucky the network is working. And then I just convert those into a time series that is regularly spaced. So in case you sample your data irregularly, that weekends are not included, for example, this is the standard way to make sure that you have a regularly sampled time series to do all kinds of processes. And the process that we do is now the following. First of all, we convert it into a time series with the corresponding magnitudes taken out, so it's not noted in US dollars or euros anymore. And we multiply silver by a factor of 100 to have roughly the same number size. And we obtain here a time series, and now I take that time series, which I call metals, and plot it. And this is the plot. This is basically the value of gold, silver, and platinum over the last 2 years, and you can see the decline. And now I'd like to know what the future will hold, so I estimate a process. And the process that I try to estimate here is an ARMA process, or differently put, it's a weak stationary autoregressive moving average process that I try to fit onto the data. Oops, no, I didn't mean to. Sorry. I did not mean to. Okay, I fit that on the data, and I get here this ARMA process now that tries to reproduce the data, and I use that process to basically do a forecast into the future for the next 3 months. And first here I can verify if that process actually is weakly stationary and if it's invertible. And if so, I can try here a forecast of 3 times 30 days, and then I can plot this. And as you can see, we do get a forecast which is quite profound. You can see that there is supposed to be quite a gain in silver price in the next few months to come. So if you trust me, please invest. If we fail, I'll blame it on the machine. Okay, so this would be one-dimensional data processing, but well, it's pretty dry. We're working with data that you can't relate to, so I quickly changed the subject and now talk about speed and sound. Well, we are in Germany, and I know, for example, that Konrad loves to take his car to Germany to do some speeding on the Autobahn. And of course, also in some places you have a speed limit here, and you can use Mathematica to measure the speed. And you can do it very simply. You just have to put up your iPhone, iPad, your computer or whatever, record the sound of the car driving by, and just by the sound of the car driving by, you can determine the speed in Mathematica. And that's what we're going to do now as a kind of a signal processing example. So the sound sample that I have here sounds like this. And what you hear is a, pardon me? That was not Konrad. That was not Konrad, no. But the sound that you hear is basically the typical Doppler effect. You have the high pitch initially, and then it goes down to a lower pitch as you first as you approach. It's a high pitch. As you leave, it's a lower pitch. And what we also have to know, of course, is the sample rate of this sound sample, which is in this case 8,192 hertz. Okay, so what we do first we have to, well, not just get the amplitudes of the sound, we have to get the frequencies. And for that, I'll do here a continuous wavelet transform with a Gabor wavelet. And this gives me kind of a visual feedback of what the sound that we just listened to looks like. You can hear basically vertically, you can see the spectrum, the different frequencies of the sound. And the x-axis is the time axis, basically going from 0 to 5 seconds. And you can see how the frequencies, being initially a little higher, drop as the car goes by. And what we need to know is now the difference in frequency initially and at the end. And even if we know the shape, we can even determine the distance by which the car missed us. So I'll try to do all of that. First of all, I don't have to have that high sampling rate, so I just downsample the whole thing by a factor of 32. And then I do something here that is a little bit complicated. I regularize first the data by Gaussian, so I average first the amplitudes before I subsample. So I basically do a proper subsampling. And then what I do here is the following. I basically have here the wavelet data at one instant of time. And I compare it to the wavelet data at the next instant of time. And I pad this, so I can do the following. I can do a correlation. And I do the correlation by shifting the scales of the next frequency or of the next wavelet timestamp. And just by moving it up and down, I can see where I can get the highest correlation. And when I get a correlation, I know how the frequency changed from one step to the next, or how the scale in the wavelet transform changed. And to exactly see how it changed, I do find peaks, because that's where I get the highest correlation coefficient. And knowing the highest correlation coefficient, I know the shift in scale. Then I accumulate the scale, and by that I know the scale shift over time, which I determine here. And then I convert the scale of the wavelet transform into frequencies. And last but not least, I do plot this. And this is the shift in a frequency or scale normalized to the average frequency. And you see initially you're about 5% higher in the frequency or the pitch, and when the car is departing, it's about 5% lower. And having this curve, this characteristic curve, I can now go ahead and try to fit the formula that I have for the Doppler effect, which I'm not going to derive here. Please just take my word for it. It's this formula for a car driving by at a given distance d, with a velocity v, and where t0 is the time where the car basically is just next to me. So I do a nonlinear fit of this model. And once I've done that fit, I can call up here the parameter table, and I can read out one by one the data. And the data reads here that the car was going 70 kilometers an hour, so not that fast really. And if you also read of D, you can see that the car missed you by about 4.7 meters. And all of that taken out just out of an audio recording. So an example for signal processing in 1D. Okay, let's slowly climb up the dimensionality ladder. And before I do so, I want to have kind of an intermediate topic, and that is the resampling, because we have put a lot of effort into resampling theory in Mathematica. And just to motivate that, I quickly repeat some very simple resampling. Well, for example, linear resampling, you probably know, just linear interpolation is pretty easy, and if you have a regular grid or regular sampling, it's nothing else but basically taking a so-called first-order B-spline or this kind of pyramid or unit triangle and always place it everywhere where you see a sample with a corresponding amplitude. And if you do that, you interpolate here, for example, just a spike data, or you interpolate any kind of data, but just adding up these pyramids under the data itself and adding it up. Well, if you do a cubic B-spline interpolation, you don't have this pyramid anymore, this triangular-shaped kernel, but you have a much more smoother one that is smooth even up to second derivative order. And thereby you get a much nicer interpolation, but actually it's not an interpolation if you look closely. It's an approximation. So you don't go through your data samples anymore, but you cut corners by doing this. And on top of it, as you can see here, it's more like a blur than an interpolation. So it's not that great. And that's why many people really think B-spline interpolation is not a great thing to do, but that's actually not quite true, because there's a step you have to add to B-spline interpolation, and that is basically undo the blurring. And undoing the blurring you can do with the built-in Z-transform in Mathematica very nicely. And please bear with me if you don't know now the mathematics that I'm applying here. I'll be back on track in just a minute, but I don't have time now to explain Z-transforms and all these things. The idea is as follows. The beta kernel, or the kernel that I apply here, has this discrete shape. It's 1/6, 2/3, 1/6 if you're on a discrete grid, and I want to undo that kernel blurring or that kernel effect if I convolve. And so what I do here is I create a Z-transform, and now for the Z-transform I just try to find the inverse and then go back to the corresponding, and out of that inverse I will construct an operation that basically will then undo the blurring. So I have here a transfer function of this, but I take the reciprocal, so that's the transfer function of the inverse operation, so of the unblurring operation. And I can even factorize that, so I basically can write that as two operations. And I can also simplify that here as a system modular series connect, so I can basically have a series of these two operations, one after another, applied, and it will do the inverse or the deblurring. And I can do that as a recurrence filter, which works nicely if you go this way. I can do it also as a recurrence filter for the second term, but that second term, if you look closely, isn't stable. It's a so-called anti-causal filter, and it will basically amplify errors and is not stable as such. But it is stable if you go the opposite direction. So in order to go the opposite direction as a recurrence filter, you have to go from Z to 1 over Z. I get this transfer function. I apply that as a recurrence filter. Now in the opposite direction, you see it's stable. And if I combine now these two recurrence filters, I have now an inverse cubic B-spline filter, which I can basically put in front of the B-spline interpolation and thereby now get perfect cubic spline interpolation, as you see here. So now you see the pre-processing this with your recurrence filter that I just developed. You now have a perfect interpolation, not an averaging in there, no blurring. And I can, wait a minute, do this also for all kinds of data, and then of course also for image data. Here, for example, I have an image of the moon, which I'd like to increase, which I'd like to resample, or image resize for that matter. And with all these commands like image resize, image rotate, image transform, they all have intrinsically a resampling method built in. And very much depending on that resampling method, the quality of the image is good or bad. Now this was just a B-spline, you see the blur. If you have now the pre-filter in there, you see a much more crisper result of the image than just doing an ordinary B-spline. And this is just kind of a motivation because we have gone to quite some length to build into Mathematica all kinds of resampling routines. So here you have a list of, how many are there? Whoops. Of 58 different resampling methods. Actually, there are more because some of them go to infinite order. And not only do you have them at your disposal when you do all kinds of image transformations, but you can call up all kinds of properties. With resampling algorithm data, you can call up the kernel function, you can call up a plot of it, you can have the effective interpolating kernel. So this was basically the B-spline kernel. If you do the B-spline kernel and the deblurring, then effectively you convolve or interpolate with this kernel. You can ask for the regularity of the result, so it's continuous up to second derivative order. The size of the kernel gives you an idea of how fast the whole thing works. You can ask for the Fourier transform of the kernel to get an idea of what the attenuation is in different resampling techniques, and so on. And just to give you another example, why it's worthwhile putting some emphasis on this. Here we go. Here I have image rotate applied several times on an image, and you see that if you just do linear resampling, the image gets blurred quite a bit. If you do Catmull-Rom, which used to be our standard one, it gets much better. And if you do for example, quintic spline sampling or OMOM sampling, you get even better result, but I doubt if you can see it on this screen, you will see it on another screen. So all of this underlying machinery is there to do signal processing in 2D. Now, a little fun example, which I will quickly bring up. This is an image processing example that adheres to the previous talk, basically getting a data bin in. So basically what I do here is I load a data bin of a camera feed that was positioned here in Champaign at the headquarters, and that was basically looking at a fish tank. Now, loading the data will take a little bit of time, so I don't want to waste that. I'll just load the data here in my notebook, and what the data looks like is as follows. It does take a lot of time, no matter what. Well, I think given the amount of time that I have left, I will skip this particular example. It's not that, and just move on with other examples since I have 5 minutes left only. So here are examples from our built-in image processing capabilities that you may not be aware of. For example, image in paint, where you can just fill in faulty areas in an image, or you can synthesize areas that are not there, basically removing people. So don't trust any image that you see anymore, because it can do amazing things with it. Another example, which I quickly like to do, is deconvolution. Deconvolution goes as follows. Basically, if you blur an image, if you don't have perfect vision, you convolve your image with a kernel. Now, in this case, I took a Gaussian kernel, and if you know your kernel very well, then you can really deconvolve to an extremely crisp result, because the data or the information is still in that fine grayscale values that you possibly have originally. If you have noise in the image, then already things go bad. And if you don't know the kernel exactly, also you're a little screwed. Now, real life image, an image from my kids. I took this image some years ago. And I love this image so much, but it has a little flaw. The guy here, my son, he's sharp, but my daughter is a little blurred. And I tried to fix that. And you can fix it by looking basically in her eye, because there you have a reflection. If it's a perfect image, it should be a point-like reflection. And from that reflection, I can deduce the kernel that blurred the image, the foreground. And from that, I can then make a sharper image. So let's try this. I'll just do a little close-up here. I basically find the location of the reflection. I read out the reflection here little bit by little, and then what I do here, I don't go through all the detail, is basically derive here a good model of a kernel, basically dampening the side a little bit, taking the average of both reflections left and right. And what I come up with is this kind of blurring kernel. So that's my blur. And now once I have that blur, I can actually deconvolve it. The deconvolution, unfortunately, produces some more noise in the image, so I do a little bit of Perona-Malik blurring, and that's the result. And in case you don't believe me that this has some benefit, I'll quickly do both before and after. And that's a typical deconvolution example. All right, and okay, since I have one more, and I'm gonna, since I know I cut into lunch here, but this is too good to skip. This is an example that you may have seen on the internet. It was really hip about 1 or 2 years ago. It was a project done by people at the MIT Image Lab. And what they did is they developed an algorithm that amplifies motion in your images, in your animation. So what you have here is just the wrist, and here I have a stack of images, and unfortunately this will apparently take a little bit of time. Here, let's bring this up a little bit. I can now run basically the movie of that wrist, and well, if you say you can't see anything, it's probably true. There's hardly any motion. There is some motion because there's a pulse, but you cannot see the pulse. And now I do all kinds of tricks to see actually the pulse in that image. So let me quickly do it or explain how it's done. The idea is very simple. If you have motion in your luminosity field, a shift, then in the Fourier space, that is basically multiplication with a complex factor. And that complex factor that I can magnify, and that's exactly how it's done. You basically convert it into Fourier space on different scales and different frequency bands, and then you amplify those complex factors that you have, and then you basically convert everything back, and that gives you your motion amplification. Here, this is the code. Well, I won't go through this. And so what I do in the code is I basically decompose the image in a pyramid of different scales and different frequencies, and I can also recompose that. And then I apply that mechanism, and at the end here, I now pre-calculated that because it takes about 30 seconds to run. You may see the pulse. I'm not sure if you can see it very well. I can make it maybe a bit bigger, the whole thing. And here you can see that with image processing, you can even make invisible stuff visible. So that's kind of an example now of 3D processing, and I think I stop here.